In this session, we are going to deal with one of the most important components of our life and an important area of syllabus in physics, that is light. The different phenomena associated with light like reflection and refraction. I'm sure you will be aware of what are the different forms of energy, isn't it? Like heat energy, light energy, solar energy, even mechanical energy, chemical energy, etc. But among all this, what that is most important and dear to us is light. Why is it so? Because light helps us to see things. In terms of biology, if somebody asks you, how are you able to see things? You may say, it's because of your eyes, isn't it? But in terms of physics, it's because there is light. What about night time? Are you able to see things with the help of an external light? Only if there is an external source of light, you will be able to see things. But during day, you are able to see the things freely and free of course because sun provides you light energy. So, light is a form of energy that helps us to see objects. How does it happen? That is, when light falls on a particular object, it will reflect the light. And this reflected light, when reaching our eyes, we are able to see the object. So, there is a term called as reflection. Haven't you noticed this? So, light possesses certain characteristics which makes it most interesting. Light always travels in straight line. But the fact is, whether it travels every time in straight lines, we need to have a discussion on that. But still, there are many common phenomena of light that is available around us in our nature. The only thing is, we may not be aware that it is because of this particular phenomena that the particular effect is happening. Like formation of shadows, formation of images in mirrors and lenses. Then what else? Twinkling of stars, the formation of the very beautiful rainbow, etc. happens due to different phenomena of light. All this is because speed of light is different in different media. So, light in our daily life possesses a lot of importance and we need to understand how light is able to produce so much beauties in our life. As you can see in this picture, there are different phenomena associated with light as being shown. The beautiful rainbow formation, the dispersion, as well as how we are able to see the objects. As we have already stated before, how we are able to see the objects. We have already told it's because of the reflection. When sun's light energy falls on a particular object, it gets reflected from that and that ray reaches our eyes and it finally leads us to see the objects. So we need to discuss in detail what do you mean by reflection. You all are familiar and you all are equal to stay in front of mirrors, isn't it? Why is it so? It's because you may like your face, that's fine, but there are still other things, isn't it? If you stand in front of mirror, if you are not able to see yourself, won't you stand before it? No. So, you like to see your reflection on mirrors. So, how does it happen? As we have already said, it's because of reflection. Fine. But does all objects produce this reflection? No. So, only the polished or highly smooth surfaces like mirrors do this reflection. So, when light falls on a highly polished surface like mirrors, the thing what happens is the light is sent back to the same medium or reflection happens. This is a kind of bouncing back of light. And this process of bouncing back of light into the same medium by a highly polished surface is called as reflection of light. That's because of this phenomenon that you are able to see your own reflection from a mirror. But all these phenomena happens according to certain laws. So that is laws of reflection. So we can infer what are the different laws of reflection. The first basic law of reflection is that the angle of incidence is equal to the angle of reflection. From the figure, you may be able to infer what do you mean by an angle of incidence and what do you mean by angle of reflection. Angle of incidence is the angle between incident ray or the ray that is coming from source of light and the normal. What do you mean by angle of reflection? Reflection angle means it is happening after the reflection. So, the angle between the normal and the reflected ray. What do you mean by reflected ray? The ray that passes outside the object once the reflection happens. So the angle of reflection is the angle between the reflected ray and the normal. So the laws of reflection states that angle of incidence must be equal to angle of reflection. The second important characteristic of or the basic quality that is to be meted for reflection of light is that the incident ray, the reflected ray, and there is also another one that is a normal or the perpendicular to the mirror at the point of incidence must lie on the same plane. In the figure, it's clear that if you look, all the three rays, that's incident ray as well as a reflected ray along with the perpendicular in between, that is a normal, at the point of incidence all lies on the same plane or they share the same plane. Only if these two criteria are met, the laws of reflection are valid. So, when we look a mirror, just a plain mirror, usually for looking a face or doing some makeups or something, we use a plain mirror. But is the mirrors only having a category of plain mirrors? We can look whether they are having some subcategories. But now we are going to discuss how the image is formed being a plain mirror. So what do you mean by a plain mirror? A plain mirror is one which is having a plain surface or a flat surface. And the features of the image that is formed by plain mirror depends on certain condition. The first and foremost condition is that for any image to be formed, there should be an object, isn't it? For example, if you look at the mirror and if you need to see the image, first of all, we must stand in front of the mirror or we must look in the mirror. In that case, the object will be us or our face. So, the object and image must be perpendicular to the mirror. That is how an image is formed in a plane mirror. And there are certain features of the image formed by a plane mirror. For example, if you stand in front of a plane mirror, what will be the formation of a mirror look like in the image? That is, the image formed will be virtual. And what is the meaning of virtual? Of course, I am sure that you will be knowing about the other thing of virtual. The opposite of virtual is real. You all like reality, isn't it? But there are also some virtual things happening. Virtual means that's bit of an imagination or that's not quite happening. We sense it in an imaginary world. So virtual image means the images that can't be obtained on a screen. So what may be real images? Real means real images are images that can be obtained on a screen. So the image formed by a plane mirror is the one which is virtual. And the image formed by a plane mirror will be upright too. Upright means it will be erect. And the image formed by a plane mirror will be having same size as of the object. And one important characteristic that you need to be concerned is that there is a twist when in case of the image formed by a plane mirror. That is, it is laterally inverted. What do you mean by laterally inverted? This can be sensed by looking at this figure. From this figure, you can infer that a person is being standing in front of a plane mirror and the other side the image is being formed. It is easily understood that the image is being laterally inverted. What do you mean by lateral inversion? For example, if I am standing in front of a plane mirror and if I am raising my right hand, then the image will be such like you are lifting your left hand. That means there is a change in the direction or there is a left-right inversion. For example, if I am raising my right hand, the image will be like the rising of left hand. And you can also infer that the distance of the image as well as the object from the center of the mirror will be same. Isn't it? That is, x1 as well as x2 is at an equal distance. So, we can see the nature of images formed by a plane mirror has certain definite characteristics. So, we can infer that the image formed will be as far behind the mirror as the object is in front of the mirror. The particular characteristic that we need to note is that it will be laterally inverted. That is, there will be a left to right inversion. So, we may be amazed how this happens when we were kids. But the fact behind this lateral inversion is due to a particular feature of image that is formed by plane mirrors in the form of lateral inversion. So now we have discussed about what you mean by plane mirrors. So in the beginning stage we had a discussion whether the mirrors are having only single type like plain mirrors. Isn't it? No. But the fact is that in case of mirrors, there are different varieties. There are plain mirrors as well as spherical mirrors. I think you all are confirmed with what you mean by spherical mirrors or sphere. In maths, you may have dealt with different types of figures like triangle, rectangle, spheres, circles, etc. So, spherical mirror, as the name suggests, it's a type of curved mirror. Plain mirror means, as we have already told, it is type of flat mirror or a plain mirror. So, spherical mirror means it is curved. So, now the question is the curve inwards or curve outwards? So, it is having two different categories like curved inward mirror and curved outward mirror. So, the spherical mirror can be said as a mirror which is a part of a hollow sphere. And it has mainly two types, that is concave mirror and convex mirror. So, concave mirrors are the mirrors which belongs to the category of spherical mirrors. And the main importance is that they are curved inwards. For example, if you are a person who is most interested in doing kitchen items, if you go to kitchen or let's say like if you are eating something with spoon, you can see they are being a concave mirror or convex mirror. Just think about it. If it is curved inwards, it can be called as a concave mirror. On the other hand, a spherical mirror whose reflecting surface is curved outwards, then it is called as a convex mirror. From the figure itself, you can see the concave mirror is one which is curved inwards and the convex mirror is one whose reflecting surface is curved outwards. So, what may be the difference between a mirror and lens? So, we need to have something more to understand what is the difference. So, as the figure suggests, there is a concave and convex mirrors. Both of them belongs to the category of curved mirrors or spherical mirrors. So, you can see there is a subheading like concave mirrors are called as converging mirrors. What do you mean by converging? Converge means to meet together at a point. And what do you mean by diverging? Diverge means to get split from a particular point. So, concave mirror is called as a converging mirror, whereas convex mirrors are called as diverging mirror. How concave mirror can be called as converging? It's because from the figure itself you may be able to understand the rays of light which are passing parallel to the principal axis after reflection from the concave mirror will meet at a point or converge to a point on the principal axis. So, the rays of light after reflection from concave mirror converges. That's why it is called as a converging mirror. So, what may be the opposite? A mirror which is capable of diverging the rays that is falling on it is called as a diverging mirror or a convex mirror. That is being clearly from the convex mirror image, that the rays of light which is parallel to the principal axis of a convex mirror, after reflection it will be appearing to get diverged from a point. Where is that point? If you look the concave and convex mirror, for a convex mirror it is behind the mirror. What in case of concave mirror? In case of concave mirror, that focus or that point is in front of the mirror. So, when we talked about the concave mirror and convex mirror, I use certain terms, isn't it? Like principal axis, rays of light, etc. So, we need to first know what do you mean by this principal axis. By looking the figure, you may be able to infer something, but we need to definitely know what does they mean in detail. From this figure, you will be able to understand what this really means. In this particular figure, you can see an object is being kept and the object's height is AB, denoted by AB. And there are so many light rays which is falling. And in the starting of the topic itself, we have stated that is it a concave or convex mirror? By looking the surface, can you tell? Because it is a concave mirror because it is being curved inwards. You can also draw such type of diagram using convex mirror that will be dealt in the later sessions. But now, for the time being, I have taken a picture of a concave mirror. So, let's explain these terms in the study based on this concave mirror. Okay. So, light rays are being incident and that is being shown by the arrows. So, it is falling on the concave mirror surface. The concave mirror is being depicted as MN, isn't it? So, and you can see another line which is denoted by CF and P. What does this stand for? So, we need to understand what does they mean. So the first term in terms of spherical mirror is the center of curvature, which is depicted by the letter C. You can see that this particular mirror forms a part of a sphere. That's what spherical mirrors mean, isn't it? Mirrors that is forming a part of sphere is called as spherical mirror. So concave mirror or convex mirror are types of spherical mirrors. So the reflecting surface of Mn forms a part of a sphere. If we extend that, it will be just like the case of a sphere. That's what it means. So the letter C depicts the center of curvature. And the meaning is that the center of the sphere of which the mirror is a part is called as the center of curvature. And there is another one called as capital F. What does that mean? We have already told in case of concave mirror it is called as converging mirror. And in case of a convex mirror it is called as a diverging mirror. In the previous diagram we have already told in case of a concave mirror, just like this diagram, the rays of light which is parallel to the principal axis after reflection meet at a point on the principal axis called as principal focus. Then what do you mean by this principal axis? You can see a line where I have marked C, F and P. C for center of curvature, F for principal focus and P for pole of the mirror. So principal axis is this particular line or straight line that is passing through the center of curvature and pole. We have already told what do you mean by center of curvature, isn't it? It is the center of the sphere of which the mirror is a part. Then what do you mean by pole? From the diagram you will be able to understand that pole is just a denotation which means the center of the spherical mirror. We have taken many different points like principal axis, center of curvature, etc. So for the mirror we are just imagining or we are just stating that the center of the sphere is denoted by the letter P or it is called as pole. And the principal axis is the straight line that is connecting this center of curvature and pole. There is yet another quantity or statement that is to be found, that is radius of curvature. Just like the center of curvature, radius of curvature means the radius of the sphere of which the mirror is a part. For example, Mn is a reflecting surface or a part of the mirror. So if I extend that, it will just form like a sphere. And if I take the radius of that sphere, it will be the radius of curvature. So center of curvature, radius of curvature, pole and principal axis. And also the principal focus are being dealt in this figure. So we need to infer what are the different quantities and how they are connected. So in case of concave mirror, it is called as a converging mirror because rays after reflection meet at a point which is noted here as principal focus capital F. What may be the case of principal focus in case of convex mirror? As we have already told, for the rays may be appearing to be diverged from that point. So it is called as a diverging mirror. So at yet another quantity that we need to understand is focal length. We have already discussed what is meant by focus, isn't it? Principal focus we have already discussed. That is, it is a particular point where appear to be converged in case of concave mirror and the particular point in case of convex mirror where rays appear to be diverged after reflection. But in case of focal length? Focal length means it is a distance between pole or P and the principal focus. What's pole or P? It is the center of the spherical mirror which is depicted by the letter P, and principal focus means in case of concave mirror it is the particular point in which the rays after reflection converge. So the distance between the center of the mirror P and the principal focus is called as focal length. And in case of spherical mirrors, whether it be concave mirror or convex mirror, there is a general mathematical equation connecting both. That is R equals 2F. Here capital R depicts radius of curvature. By the way, what was radius of curvature? It simply means the radius of the sphere of which the mirror is a part. And small f means focal length. The principal focus is being depicted by capital F, but the small f denotes focal length. So from this diagram, you will be able to understand what are the different quantities. That is, here the center of curvature is depicted by C, the pole is being depicted by capital P, the principal focus by capital F, and radius of curvature was the distance between distance between the mirror and the radius of the sphere which it is forming a part. So it is CP, that is between the pole or center of mirror and the C, that is being the center of curvature. So what do you mean by principal axis? We have already told principal axis is the line that is connecting the center of curvature and the pole, that is XY. And focal length means it is the distance between the principal focus and the pole or center of the mirror, that is PF, which is depicting the focal length. So these are the main terms that is important in case of study of spherical mirrors, whether it be a concave mirror or convex mirror. By looking the diagram, you will be able to understand that all these rays are parallel, isn't it? We have already told that light in case of common areas, it travels in straight line. Only when specific conditions are occurring, light deviates its path. So now we need to understand how the images are formed by spherical mirrors. This is easily depicted by using ray diagrams. But when you draw ray diagrams, you need to be careful to indicate whether it's incident, whether it's reflected, etc. So arrows form a very important part in case of ray diagrams. So we need to understand how ray diagrams happens in case of a concave as well as convex mirror. So what was the main difference between concave and convex mirror? For a concave mirror, the rays after reflection converge to a point called as principal focus. But what in case of a convex mirror? It is a diverging mirror, isn't it? For that, in a convex mirror, rays of light after reflection will appear to diverge from the principal focus or the point behind the mirror. So, as you can see in this particular figure, for the concave mirror as well as convex mirror, I have shown it simultaneously. So, it will be easy for you to compare and study. Okay. So, in case of concave mirror, the rays of light parallel to the principal axis after reflection pass through the focus. But in case of convex mirror, they appear to diverge from the focus. This was a statement that we have already discussed. So, we need to know which are the more important further things in case of concave and convex mirror. So, next one is that in case of a concave mirror or converging mirror, the rays of light which is passing through the focus. What was focus? Principal focus means it is a particular area in which rays converge, isn't it? In case of concave mirror, but in case of convex mirror, they diverge. So, in a concave mirror, a rays of light passing through the focus after reflection will be going parallel to the principal axis. And what was principal axis? Principal axis is the straight line connecting the center of curvature and the pole. What happens in case of convex mirrors? Here you can see in convex mirrors, the rays of light directed towards the focus after reflection goes parallel to the principal axis. So, it happens simultaneously. Only thing is that one is concave or converging mirror and another one is convex or diverging mirror. And for them, the reflecting surfaces are of different nature. The third point is that how the concave mirror or convex mirrors light rays behave after reflection if they are passing through center of curvature. So, what was center of curvature? If you take a concave or a convex mirror, if we extend them, it will be forming just like a sphere. But we have shown only a portion of them, isn't it? So, if such a sphere exists, then that will be having a center. So, that is termed as center of curvature. So, for a concave mirror that is curved inwards or a converging mirror, as we say, if a ray of light is passing through center of curvature, after reflection also, it will be passing along the same direction. In the first figure of concave mirror, you can see it. If you look at it, you can see the forward moving arrows and the backward moving arrows are along the same line. That means, if the light rays are being reflected, it will be reflected along the same path from which it has come through. So, the light will be passing to the same center of curvature before reflection as well as reflection. And in case of convex mirror also, same thing happens, but only thing is that the mirror will be curved outwards and it will be a convex mirror. And the next point regarding concave and convex mirror is, in case of concave as well as convex mirrors, the rays of light which is obliquely at the pole will be reflected obliquely, but they will make equal angles. In this particular figure, whether it be concave mirror or convex mirror, you can see they will be making the incident as well as the reflected rays will be making equal angles. Like angle of incidence and angle of reflection are equal. That's what we said in the starting also, isn't it? Angle of incidence must be equal to angle of reflection. So what differs is that how the concave and convex mirrors appear. That's what difference. One is curved inwards and one is curved outwards, and the focal length as well as the center of curvature, focus, etc. differs. If you take in case of concave mirrors, the object is being placed in case of its left side. And what in case of convex mirror happens in a little bit different manner. So first we need to understand how the image formation happens in case of concave mirrors. So in order to study the image formation in concave mirrors, there are different positions. But to have a clear idea of what happens in case of concave mirrors, you need to clearly know the things that we already stated, like different terms. What do you mean by center of curvature? What do you mean by principal focus? What do you mean by pole? What do you mean by radius of curvature? Focal length, etc. So I'm sure by looking into the previous sections, you will be able to understand what are the different terms, isn't it? If you're thorough with that terms, I'm sure you will be easy to understand all these ray diagrams. But when you draw the ray diagrams, you must be careful that you indicate it with arrows. Whether it be the incident ray or the reflected ray, you must be able to understand it in a proper manner. So here also, first we are discussing about concave mirrors. So what were the peculiarities of concave mirror? Concave mirrors are those which are converging mirrors. So here I have taken the reflecting surface of a concave mirror by a portion MN. Okay. So I am placing my object. For any mirror image formation, there must be an object and there must be an image, isn't it? So I am first placing my object. The object is being denoted by AB. An object of height AB is being taken and it is kept at infinity. So I am keeping an object at infinity. Then we need to know what happens after reflection. How the image is formed, where it is formed, what is the nature of the image, etc. So, in case of a concave mirror, if an object is kept at infinity, the image, as you can see here, the rays of light going parallel to principal axis after reflection passes through the focus. And the image form is highly diminished, real and inverted. But if you look at the picture, you can see the image is not being shown, isn't it? Only AB is being shown. There is no another thing of image of A dash or B dash here. Why is it so? As we have already stated, it is highly diminished. So, since it is highly diminished, it can't be shown on a ray diagram. But the fact is that any such diagrams or any such images formed which is highly diminished will be always real as well as inverted. The another kinds of positions of objects will make you clear how these things happen. The second position of the object in case of a concave mirror image formation is when the object is beyond C. So what was C? C is the center of curvature. So as you can see here, AB denotes the height of the object. And what is the height of the image? We need to understand. So from AB, the image, from the height of the object, the ray of light is being passing, and when it touches the surface of the concave mirror, after reflection, what happens is it passes to the focus and another light ray from the same AB passes through center of curvature and finally they meet together to form the image between C and F. What do you mean by C? C is the center of curvature. And what do you mean by F? F is the principal focus. And you can see the image is being formed. So the image is being denoted by A dash, B dash. And how is the nature of image obtained? It is seen as diminished, real and inverted. So for the first set we have already told, if the image is being diminished, it would be real and inverted. So just like that, here also it is diminished, real as well as inverted. So when the object is beyond C, the image will be formed in between center of curvature and focus, and the nature of image is that it will be diminished, real and inverted. What do you mean by real? Real means An image that can be obtained on a screen is called as a real image. Inverted means it will be in the inverted position or upside down. So the next position is when the object is at C. So you can see here the object is being placed at C and MN is a concave mirror. So the object is being placed to the left side of the mirror as AB. So the light rays are being forming from AB. So when it touches the surface of the concave mirror, after reflection, they pass through the principal focus. And where is the image formed? The image is formed at the center of curvature itself. But what is the nature of image formed here? You can see the nature of the image is that it is represented by A dash, B dash. So A dash, B dash is the image. And if we compare AB and A dash, B dash, how is it comparable? We can see the same size of the object is being taken by the size of the image. And also the image is being real as well as inverted. So when an object is placed at C, the center of curvature of a concave mirror, the image is formed also at center of curvature. But the thing is, the object and the image will be having same size, but the image will be real and inverted. Real means that can be obtained on screen. Inverted means it will be just upside down, but has the same size as that of the object. So the fourth position for image formation in a concave mirror is when the object is between C and F. As you can see in the ray diagram, if the object AB is being kept in between center of curvature and principal focus. So the light rays from the object falls on the mirror after reflection. They will be meeting and forming the image as A dash, B dash. So where is it formed? So the image is formed beyond the center of curvature anywhere. So how is the image formed, or what is the nature of the image? The nature of the image is that it is enlarged. If we compare AB, the height of the object, and A dash, B dash, the height of the image, you can see A dash, B dash is much enlarged or much more in size, isn't it? So the size of the image will be more when compared to the size of the object. And also the nature is that they will be real as well as inverted. So when we place an object in between C and F for a concave mirror after reflection, the image is formed beyond C on the same side of the mirror. And what is the nature of image? They are enlarged, they are real and inverted. So let's look at the next position. The next position is depicted when the object is at F. You can see I have placed my object AB at principal focus of the concave mirror. So what happens? Light rays from the particular object goes and hits the concave mirror. After reflection and passing through the principal focus, the object is formed. But can you see the object image anywhere? No, you can only see, or depicted in the diagram is AB, that is the object of height of AB, isn't it? You can't see the image of the object. So where did it go? The thing is, there is the image formed, but you can see because you are not able to see it because it is at infinity. Infinity means there is something present but you can't see it. It is at a very large distance. So when the object is at F or principal focus of a concave mirror, after reflection, the image will be formed at infinity. And how will be looking at it? It will be, the image will be formed very enlarged, but the nature of the image, just like other cases, they may be real and inverted. It can't be shown in the diagram, that's why we haven't shown. But the fact or the clear result is that the image formed will be real as well as inverted. So what was the meaning of real image? The image that can be obtained on a screen. So the ray diagrams that is passing through C has an arrow to infinity. So that is what we can infer from this diagram. So the final position is when the object is between F and P. So I have placed my object AB between F, principal focus of the concave mirror, and pole of the concave mirror. So when is the image formed, or where is it formed? You can see When I have placed the object AB between principal focus and pole of the mirror, what is the image formed? The image is being depicted as A dash B dash. Where is it formed? It is formed behind the mirror, isn't it? But what was the case of other cases? For all other cases, the image was also formed on the same side of the object. For example, if I have kept the object in the left hand side of the mirror, then the image was also formed on the left hand side of the mirror. But what is in this case? In this case, you can see I have placed my object AB on the left hand side of the mirror. But where is the image formed? The image is formed on the right hand side of the mirror or behind the mirror as A dash B dash. If you compare AB and A dash B dash, what can you infer? You can see the image formed is enlarged or bigger in size. Is it real and inverted? No, it is not inverted, but it is straight, upright, or it is erect. And it is virtual. So a virtual image will be forming an erect image also. So when I keep the object between focus and pole of a concave mirror, the image will be formed, but where is it formed? It is formed behind the mirror. And the nature of the image is that it will be virtual, erect, as well as enlarged. This table summarizes the image formation by the concave mirrors for different positions of objects. From all the ray diagrams that we have discussed so far, you could have understood how the size and nature of the images differs. So, from these figures and the ray diagrams, only for the sixth position, when the object is kept between P and F, the nature of the image is as obtained as virtual and erect. For all others, the nature of the image obtained is real and inverted. So, at infinity, when the object is kept, the position of the image will be at focus F and the nature will be real and inverted. The size of the image will be highly diminished and point-sized. If the object is beyond C, then the image will be formed between F and C. And how will be the size of the image? It will be also diminished. And the nature of the image will be real and inverted. When the object is at C, then the position of the image will be also at C. What will be the size of the image? It would be same size. And what is the nature of the image? It will be real and inverted itself. So when the object is at between C and F, the position of the image will be beyond C and the image will be enlarged, real and inverted. When the object is at F, then the position of the image will be at infinity. And vice versa. When it is at infinity, the object, then the image will be at F. So, the size of the image, when the object is at F and the image is at infinity, will be highly enlarged, real and inverted. So, you need to take special concern for the sixth position. That is, when the object is placed between P, that is pole of the mirror, and F, the principal focus, the position of the image will be behind the mirror. And that too will be enlarged or of high size, and that will be virtual as well as in an upright position or erect positions. So now we need to understand how the image formation happens in case of a convex mirror. So what was a convex mirror? By looking at the diagram, you will be able to infer a convex mirror is the one which is curved outwards. And where is the object kept? The object is kept at left hand side, but the image is formed on a different side, or the rays are appearing to be coming from behind the mirror. So in this case, the object is being kept at infinity, which is represented as AB. What is the image formed? Can you see any image as A dash B dash? No. So the image is formed at F behind the mirror. You can't see an image as A dash B dash because it is highly diminished or very small size, and such an image would be always virtual and erect. As you can see, the rays after reflection appear to come from behind the mirror of the point as principal focus, which is lying on the principal axis. The second position in a convex mirror image formation is when the image is formed behind the mirror. But where is the position of the object in this case? Here I am placing my object AB between infinity and pole. So the P represents the pole of the mirror. MN represents my convex mirror reflecting surface. Here you can see the convex mirror is curved outwards, and the object is being kept on one side and the image is formed on the other side behind the mirror. So the object is kept in front of the mirror as AB and the image is formed as A dash B dash on the another side as A dash B dash. And when you compare the size of the image and size of the object, how can you infer? You can see that the image is formed behind the mirror, it is diminished, it is virtual and erect. So a general conclusion that we can make from the image formation by convex mirror is that when the object is at infinity or if it is between infinity and pole of the mirror, the size and the nature is almost the same. That is, they will be highly diminished as well as virtual and erect. Only the position changes. So a general nature of image formation by convex mirror is that they will be diminished, virtual as well as erect. So now we need to understand what are the uses of concave mirrors and convex mirrors, the different types of spherical mirrors. So we have studied what are the different sizes of images, nature of images, how the positioning of objects are taking place in concave as well as convex mirrors. So both these concave and convex mirrors are of great importance in our daily life. We can look how they influence the daily life applications. So in case of concave mirrors, they are called as the converging mirrors, isn't it? That is, the rays of light passing parallel to the principal axis after reflection converge to a point called as principal focus in case of concave mirrors. Since they are called as concave mirrors or the converging mirrors, they have a lot of applications in our daily life, especially in case of medicinal fields. So concave mirrors are mainly used in torches, searchlights and headlights of vehicles. Why do we use them? It's because to get parallel beams of light, concave mirrors are being used. And they have a converging property too. And the shaving mirrors that your father or your brothers or your siblings use are also made of concave mirrors. Why is it so? It's because to get a larger image of the face. And this is because for the concave mirrors, you may be remembering most of the images formed are enlarged image, isn't it? So to get larger images of the objects, you use concave mirrors. And also the dentist, to see the larger images of your teeth, they use concave mirrors. And large concave mirrors are also used to concentrate sunlight that produce heat in case of solar furnaces. So concave mirrors find a lot of applications in case of the daily life. So now we need to understand what are the uses of convex mirrors. So concave mirrors are having a complementary as convex mirrors. So convex mirrors are mainly called as diverging mirrors, isn't it? They are curved outwards. So convex mirrors' general image formation natures were that they form diminished as well as virtual and erect images, isn't it? So convex mirrors are mainly used as rear view mirrors in vehicles. So in the diagram you can see the mirrors which are fitted on the right sides or on the both sides of your vehicles are usually the convex mirrors. Why convex mirrors are used? Because they have a wider field of view when compared to the plane mirrors. So convex mirrors also gives erect and diminished images of the object as well as a wider area of view. So they are mainly used in cases of rear view as in case of vehicles and also as a safety measure in case of vehicles. So convex mirrors find more applications since they give a erect, diminished as well as virtual image also along with the wider field of view when compared to other mirrors. So we need to understand how spherical mirrors reflection is being formed, the images are formed, etc. But certain sign conventions are also formed in case of different spherical mirrors. So we need to understand them properly. By looking this diagram, you can see there is depicted a concave mirror of reflecting surface Mn and so many facts are being depicted. So in order to consider how sign conventions are taken, we need to understand a fact. So in this figure you can see all the distances parallel to the principal axis are measured from the pole of the mirror. So there is a center of the mirror called as pole of the mirror. By keeping pole of the mirror as the center, we measure the distance. So for example, if I take 0 as my point, anything that is going further or forward from 0 as +1, +2, +3, minus, etc. minus to the other side and plus to the forward side, I would take all the positives as coming as +1, +2, +3, etc. But if I take in the negative direction or in the left hand side of 0 as -1, -2, -3, etc., they are taking signs of negative. Just like that, if I consider P, pole or the center of the mirror as my origin, then the distances which is measured to the right side of the origin will be taken as positive x-axis, and that is taken and the negative side will be taken as negative. So the distances which is measured to the right side of the origin along the positive x-axis is taken as a positive value. Just like after the 0 to the right side, we take as +1, +2, +3, etc. All the distances measured to the right side is taken as positive. But all the distances which is measured to the left side of the origin is taken as negative. Another one is that if we take the principal axis x dash, the distances measured perpendicular and above the principal axis is taken as positive. For example, if I am placing the object AB and it is on the principal axis and above and perpendicular means it is a positive one. And the distances which is measured perpendicular but it is below the principal axis, that is along the negative y-axis, it is taken as negative. So the object, as you can see from this figure, it is always placed to the left of the mirror. This means light is coming from the object that falls on the mirror always from the left hand side. So these sign conventions are always very important, and this arrows mark how we can find the directions of incident light, how the distances are measured, how the height is being measured or given different sign conventions. So we need to understand the mirror formulas. Now we have finally found out the different sign conventions, the different terms related to concave and convex mirrors, how the image formation happens in concave and convex mirrors. Now the very important mirror formula, that is we have to find out now. In case of spherical mirrors, there are certain quantities or certain objectives that we need to fulfill. It depends upon the object distance, image distance and focal length. So U is representing the object distance, that is the distance of the object from pole or center of the mirror is called as object distance, and V represents the image distance. What may be the image distance? We have already told for everything we take the origin as pole or center of the mirror, isn't it? So the distance of image from the pole of the mirror is called as image distance. So what was focal length? The distance of the principal focus from the pole. So for anything to consider, we consider pole of the mirror as the center. So distance of principal focus from the pole is called as focal length. So the relationship that connects between these three quantities, that is U, the object distance, V, the image distance, and F, the focal length, is that 1 by V plus 1 by U is equal to 1 by F. That is 1 by image distance plus 1 by object distance equals 1 by focal length. So what was focal length? Focal length is the distance between the center of the mirror, pole, and the focus or the principal focus. So the next one is the magnification formula. What do you mean by magnification? To magnify means to enlarge or make it big, isn't it? For example, for what we use a microscope? We use it to magnify things, isn't it? To see the smallest objects as big, we use the microscopes. So there is also magnification formulas for mirrors. So it is mainly based on height of the image and height of the object. For image formation, always we have two components, isn't it? One is the object and another one is the image. So we need to consider the height of the image as well as the height of the object. So it is expressed as a ratio of the image to the height of the image to the height of the object. So magnification m is the ratio of height of the image, which I represent as h dash, to height of the object, that is represented as h. You can give any representation. For example, height of the image can be represented by hi and height of the object can be represented by ho. That's according to your convenience. But the general formula is magnification m is the ratio of height of the image to height of the object. And in terms of object distance and image distance, in case of mirrors, it takes the formula magnification m is equal to height of the image is to height of the object equals minus v by u. That is minus of image distance by object distance. So that is the general formula of magnification in case of spherical mirrors. So till now we have dealt with very important phenomena of light called as reflection. There is yet another very strong and powerful one of phenomena of light, that is refraction. I am sure you will be dealing with refraction examples in your daily life, but the thing is that you may not be aware that the cause for such phenomena is refraction. For example, if you take a glass of water and you place one lemon in it, and you can see when you look from side, you can see the lemon size will be appearing to be in a different manner if it is taken outside and if it is taken inside the water. It's because there is some changes happening. Or for example, we can say, if you take a glass of water and you insert a coin in it, and if you look at the coin in the water that is placed, you can, if you are trying to pick the particular coin, you can see you may not pick it in the first try itself. Why is it so? It's because the object appears to be raised than actually it is inside the water. That means some illusion happens, isn't it? So that is because of refraction of light or bending of light. So we have stated in the first one that light always travels in straight line. But what happens when light enters from one medium to another? Is there anything happens? So that is explained by refraction. When light travels from one transparent medium to another, it gets bent or it suffers some bending. This bending of light is called as refraction. So there are mainly two different cases. As you can see in the picture, first one and second one is having a normal drawn. So light is entering from different medias. In the first picture you can see light enters from a rarer medium to denser medium. So when light travels from a rarer medium to a denser medium, you can see as in the first picture, it bends towards the normal. The normal is being depicted at the center. So the layer of light after the refraction is bent towards the normal. But what happens in the other case? When light travels from denser medium to the rarer medium, then it bends away from the normal, isn't it? So when you compare and contrast the first and second pictures, you can understand they are having different ways of expression. One is bending towards the normal and in another one, the light is bending away from the normal. So now we need to understand how refraction of light happens through a rectangular glass slab. Now we have taken a rectangular glass slab and in this, the incident ray is being depicted by AO and the refracted ray is depicted as it turns out from the rectangular glass slab as BC. So angle of incidence is being depicted by I, angle of emergence is being depicted by E. So incidence means the incident ray. So angle of incidence means it is the angle between the incident ray and the normal. Emergent ray means it is the angle between the emergent ray and the normal. So we need to understand how refraction happens through a rectangular glass slab. So there are mainly three rays in case of refraction of light through a rectangular glass slab. There is first one, the incident ray. Then the second one, that is a refracted ray, which is the phenomenon that is happening actually inside the rectangular glass slab. And the third one, that is an emergent ray that is emerging out of the glass slab. So mainly there are three rays, the incident ray, the refracted ray inside the glass slab which undergoes the refraction, and third one is the emergent ray. So what happens is that when a ray of light passes through a rectangular glass slab, it gets bent twice, because when we place a rectangular glass slab, there will be two medium. One is air and one is glass, isn't it? So the first interface is between air to glass, the ray of light or the incident ray is entering. And once the ray of light enters from air to glass and inside the glass slab, it suffers refraction or bending of light. And after the refraction, it gets out of the rectangular glass slab as the emergent ray. In that case, the ray goes from glass to air, which is the second interface. So there are basically two interfaces. First one is the air glass interface and the second one is the glass air interface. So there is bending twice at both this interface. So one bending is at the air glass interface and the second bending is at the glass air interface. So if we look at the emergent ray, that is BC, you can see if you extend the incident ray, that is OA, and if you extend it, you can see a surprising fact that the emergent ray BC and the extended ray of incidence are having a connection with them. What is the connection? The connection is that the emergent ray will be parallel to the incident ray. Only thing is that it is displaced through a distance, isn't it? So if you look at the emergent ray, that is BC, and the line that we have extended from the incident ray with dotted lines, you can see there will be a small lateral displacement only, but both of the lines will be parallel to each other. So this is the case in case of refraction of light through a rectangular glass slab. The emergent ray which emerges out of the rectangular glass slab after refraction will be parallel to the incident ray. Only thing is that there is a lateral displacement happening. So we need to understand what are the different laws of refraction of light. We have already known and understood what are the different laws of reflection of light, isn't it? That is, angle of incidence equals angle of reflection. And the incident ray, the normal and the reflected ray all lie on the same plane at the point of incidence. But what happens in case of laws of refraction of light? The first one is that just as a synonymous to the reflection of light, the incident ray here instead of reflected ray, it is refracted ray. So the incident ray, refracted ray and the normal to the interface of two transparent media at the point of incidence lies in the same plane. In case of reflection, we need not specify what is a medium, isn't it? Because light doesn't have any bending. But in this case, we need to specify it since light suffers some bending. So first one is that incident ray, refracted ray and the normal will be lying on same plane. What is the next point? That is, we need to consider the ratio. That is, angle of incidence and angle of refraction. So if we take the ratio of sine of angle of incidence to the sine of angle of refraction, it would turn to be a constant. So this is being represented by sin I by sin r equal to a constant. That is, sine of angle of incidence to sine of angle of refraction will be a constant. And this constant value is called as the refractive index of second medium with respect to first. So we have already known that the speed of light is different in different media. So refractive index is the ratio of speed of light in air to speed of light in medium. So we know the speed of light in air is 3 into 10 raised to 8 meter per second. So if c is the speed of light in the air and v is the speed of light in the medium, then how do we find the refractive index of the medium? It is given by ratio of speed of light in air to speed of light in medium represented as n equals c by v. So if you need to find the speed of light or speed of light in air or medium ratio is taken, then you can find the refractive index. For example, if you need to find the refractive index of diamond, how do you find? Of course, you know the numerator side, isn't it? That is speed of light in air, that is constant, 3 into 10 raised to 8 meter per second. And if you know the speed of light in diamond, you can take the ratio and you will be able to find refractive index of the diamond. So this is how you find the refractive index of medium. So if you need to find it specifically, you can take, in this particular figure, you can see medium 1 and medium 2. Which is the medium 1? It is the air or the atmosphere. So from the air, the right hand, the light ray enters the glass, that is the medium 2. So from air to glass, the light enters, that is OA represents the incident ray, and inside it, the glass, the refraction take place. So if I consider a ray of light that is traveling from medium 1, that is air, to medium 2, as shown in the figure, and I suppose that the speed of light in the medium 1 air is V1, then what would be the other? V2 will be the speed of light in the medium 2. So if you need to find the refractive index of the medium 1 with respect to medium 2, which is denoted as N12, it is given by ratio speed of the light in medium 2 and to the speed of the light in medium 1. That is, N12 is equal to speed of light in medium 2 by speed of light in medium 1, which equals V2 by V1. How does it invert in case of V? It is because, as we already know, N equals C by V. C is always a constant, isn't it? So when we take the proportion, in case of N12, it becomes equals to V2 by V1. So N12 equals speed of light in medium 2 to speed of light in medium 1 equals V2 by V1. So N12 is equal to V2 by V1 is a general formula to find the refractive index of a medium with respect to another. Just like mirrors, there is another category called as lenses. So a spherical lens is a lens which is of the form of a sphere part. So a spherical lens can be said to be a transparent material, but its importance or its specification is that it is bounded by two surfaces. But what was the case of mirrors? It is having only one surface as reflecting, but here we take two surfaces. In that case, the two surfaces, among them either one or the both can be spherical. The spherical lenses are mainly of two types. They are convex and concave lenses. In case of mirrors, you may be remembering, concave mirror was called as converging mirror. Convex mirror was called as diverging mirror. But what is in this case? In this case, a convex lens is called to be converging lens. A concave lens is called to be diverging lens. As you see the picture here or the figure here, you can see the convex lens. It would be thick in the middle and thinner at its edges. So a ray of light parallel to the principal axis after refraction through a convex lens will meet at a point or converge on the principal axis, as you can see in the figure, converging lens or convex lens. So what would be the counterpart? If you look the other side, the concave lens, it is thinner in the middle and thicker at the edges. So a ray of light which is parallel to the principal axis after refraction gets diverged and appear to come from a point on the principal axis on the same side of the lens. So what was in case of mirrors was just inverted or opposite here. Here the convex lens is the converging lens and concave lens is the diverging lens. So concave lens and convex lens are having a lot of primary applications in our day-to-day life as well as commercial as well as industrial products. So we need to understand how the image formation happens. So which kind of lens is this? It is a convex lens, isn't it? So it is, what was the specification of convex lens? Convex lens is thick in the middle and thin at the edges. So I need to find how the image formation happens in convex lens. Here you can see that in case of a mirror, there was only one reflecting surface, isn't it? So to the left hand side, I am placing my object and there was C, F and P. C represents center of curvature, F represented the principal focus and P represented my pole or center of the mirror. But what is in this case of lens? In this case of lens, you can see there are two focuses, that is two F1s two 2f1s also, isn't it? So there is f1 and f2 on both sides, 2f1 and 2f2 on the other side. So that means corresponding to f there are 2 1s, corresponding to 2f also there are 2 1s. It is because when we compare to the mirrors, they have only one reflecting surface, but here there are 2 surfaces. So on both sides of the lens there are focuses. So when I place my object at infinity, then the image is formed at the focus, but it is on the f2, which is on the other side. And what will be the nature of the image? It would be highly diminished, real as well as inverted. So the only difference that we see in case of ray diagrams of a mirror or a lens is that the center of a mirror is called as pole, which was represented as P. But what is in case of a lens? The center is represented by O or optical center. So right side will be having F2 and 2F2 and C2. That will be, there will be 2 center of curvatures, 2 F's and 2 2F's. So to right hand side I have my F2, 2F2 and C2. What is for the left hand side? For the left hand side of the optical center or the center of the lens, I will be having F1, 2F1 and C1 since the lenses have 2 surfaces. So if I place my object at infinity, the image will be formed at focus F2 on the other side. What would be the nature of the image? It would be highly diminished, real and inverted. So the general thing is that the real and inverted image would be formed. So let's look at the second case. So in this particular figure, you can see the object is placed beyond 2f1. As in case of lenses, there are 2 reflecting surfaces. To the right hand side and left hand side of the lenses, there would be center of curvatures, focus as well as 2f components. So to the right hand side, the image is formed and left hand side, the object is being placed. So when the object is placed beyond 2f1, as you can see, the object is termed as AB of height. And the rays of light are going from the object, and after passing through the lens, after refraction, on the other side, the image is being formed between f2 and 2f2. And what is the nature of the image? You can see, comparing to AB, that is height of the object, the height of image A dash B dash is little bit less, isn't it? So it is little bit diminished. So what is the other natures? You can see, compared to the object AB that I have placed, after refraction, the image formed A dash B dash is inverted as well as real. What was the meaning of real image? Real means it can be obtained on a screen. Inverted means it is just reverse the position. Instead of AB being formed as upright, the A dash B dash is formed upside down. So this is one peculiar feature that real and inverted image is also formed here. So we need to understand the third case. Here you can see the object is being placed at 2f1, that is to the left hand side of the lens. And what is the image being formed? The image is formed at 2f2 on the right hand side. And how do you infer the changes between object and the image? The object is being said as AB. And what about the image? It is A dash B dash. You can see when I place my object at 2f1, then the image is formed at 2f2. And how is this comparable? You can see the image formed is having same size as that of the object AB. And what is the other nature? It is also real and inverted. So optical center O represents the center of the lens, and to both sides we have center of curvatures and focuses. So the fourth position is that I am placing my object between 2f1 and f1. And when I place my object between them, where is the image formed and how is its nature? You can see the image is being formed in the other side. On one side I have placed my AB picture or AB object. So from the object the light rays are coming, passing through the lens, and after refraction the image is formed on the other side as A dash B dash. So when the object is placed between 2f1 and f1, the image is formed beyond 2f2 on the other side as A dash B dash. So if you compare the object size AB and the image size A dash B dash, what can you infer? it's quite obvious that the image is enlarged or it is being in a bigger size. And what is in the general nature as others? It is also real as well as inverted. So the fifth position, as you can infer from the figure, it is that when the object is kept at F1, the image is formed somewhere but we can't see it so. Where it may be? Obviously, it may be at the infinity. If we don't specify where it is formed, of course, it may not be able to see in the picture or diagram, but it will be formed at some further distance that it is at infinity. So, any object which is placed somewhere and if the image is formed at infinity, it would be a highly enlarged one, real as well as inverted. So, from all these positions of object, you can infer that the image was formed as real and inverted, but the size is only differed. So the sixth position and final position, which is having a slightly different change from others, is that for all others, the object was kept at one side of the lens and the image was formed on the other side. But what about this case? You can see, I place my object AB in between F1 and my center of the lens, optical center. And what is the image formed? You can see the image is formed on the same side of the lens. Only thing is that there is a difference in its size. It is enlarged, virtual and erect. So when I compare my AB, that is height of the object, and A dash B dash, the height of the image, you can see the figure that AB and A dash B dash have some resemblance. It's because they are formed on the same side of the lens. But the difference is the image will be virtual and erect. Erect means it is in a straight position or upright. And it is enlarged or it is having a magnified image. So from these 6 positions of object, you can get to a general statement that for most of them, the nature of the image formed was real and inverted. But only in this position when my object was kept, the image had a different nature as virtual and erect. The following table summarizes the image formation by convex lens. Just like what we have done in case of concave mirrors, here also there is a particular deviation or a particular instance where there is a slight difference. So there is an exception when I kept my position of the object between F1 and optical center 0, I obtained my image as virtual and erect, and also it was on the same side of the lens as that of the object. For all others, they share a common nature as the nature of image is real and inverted for all other positions of the object. So, the convex lens in a general case are found to be converging lens, isn't it? What was in case of concave lens? They are called as diverging lens, isn't it? And this main specialty of concave lens is that they are thin at the middle and thick at the edges. So, I am placing my image, I place my objects to get the image in case of concave lenses. So, I am placing here my object at infinity. How does the image formation happens? You can see the image will be formed at the focus F1 on the same side of the lens, isn't it? From the figure you can understand, I have placed my object is at infinity. You may be wondering why you are not seeing the object, isn't it? Why is it so? We have already said that when something, even if it is an object or an image, if it is not shown in the figure, that means it is kept at infinity. Or we imagine that object or that image is at infinity. We can't see what is happening in infinity, right? So, when I place my object at infinity, the image is formed at the focus F1, isn't it? So, when you look at the particular lens, you can see it is appearing to be diverging from a particular point called the principal focus. That's a speciality in case of concave lenses. So, the image is also formed on the same side. To your excitement, you may be able to see that there was no object and also there is no image being shown. So, if the image is not shown means it will be highly diminished or very small in size. And what was general nature of diminished images? They would be virtual and erect. So, this is the image formation that is happening in case of a concave lens when I keep my object at infinity. So we need to look the second case. Suppose I am placing my object. In the earlier case, we placed it at infinity, isn't it? But to here, I am making it somewhat specific. I am placing my object between infinity and f1. How does the image formation happens? You can see the image is also formed on the same side of the lens as you can infer from the figure. And how is the nature of object and image related? You can see the height of the object is represented as AB. And how is the height of the image? It is A dash B dash. Compare AB and A dash B dash. How can you infer? You can see the object and the image is on the same side of lens. And what is the nature of image? It is also diminished. And what is its position? It will be virtual as well as erect. So we can summarize the image formed by concave lens in both these cases. Whatever be the position of object, whether it's at infinity or between infinity and optical center of lens, the nature of image formed is always virtual and erect as well as diminished. So when we look the concave mirrors, concave lens, convex lens, everything, the natures of images having altogether some similarities. Only the case is that in certain positions of object there will be some exceptions. So just like the sign convention for the mirrors, there are also sign convention for spherical lenses. So only difference is that in case of mirrors, we have always the distance object distance that is being measured from the center called as pole or P. But what is in case of a lens? We call the center of a lens as optical center or O instead of the pole of the mirror. That's the only difference. For all others, it is the same. And the focal length of a convex lens is always taken to be positive and the focal length of a concave lens is taken to be negative. So, the positive focal length is being assured to convex lens and the negative focal length is being assured to the concave lens. So, in order to understand the mirror formula, we had all these matters in case of mirrors. Just like the mirror formula, there is also a lens formula. So, we need to understand the lens formula for spherical lenses. In case of mirrors, it was 1 by V plus 1 by U equals 1 by F. So, what was this U, V and F? U specifies the object distance. What was V? V specifies the image distance. What was F? It was the focal length. The same things applies for lens also. The only thing is that there differs in case of a sign. So, lens formula for spherical lens is that 1 by V minus 1 by U gives 1 by F. That is 1 by image distance minus 1 by object distance gives you the reciprocal of focal length. So, what was about magnification? What is the meaning of magnification? Magnification means it is being magnified or it is being enlarged than the actual one. So, in case of a spherical lens, the same as in case of mirrors, the magnification is found by the ratio of height of the image to the height of the object form. So, in case of mirrors also we took it, isn't it? M is equal to H dash by H or Hi by Ho, that is height of image to height of the object. That is same here also simultaneously, but only the difference is when it comes into the case of representing in terms of object and image distance, a difference happens here. In case of magnification for spherical lenses, M is equals Hi by Ho. I took Hi as the height of image form and Ho as the height of the object. So, magnification in case of lens can be derived as the ratio of height of image form to the height of object. But what is the difference here? You can note from the equation like magnification M equals Hi by Ho equals V by U. But what was it in case of mirrors? In case of mirrors, it was minus V by U, isn't it? So, in case of magnification related to lenses, M equals V by U, and in case of mirrors, it equals M equals minus V by U. So, some of the factors that we need to understand when we consider magnifications of lens is some of the important points. We know magnification means it is a ratio of height of the image to height of the object. It's fine. So, we need to understand how this magnification takes the mathematical numbers. Suppose I can say that if the magnification is represented by m, small m, it will be having a magnitude greater than 1, then the image is larger than the object. It's obvious that if you take the ratio, if I say to you that if m is greater than 1, then you must understand or you must infer from the ratio that image is always larger than the object. So what would be in the other case? If I say m is less than 1, that is magnification m has a magnitude less than 1, what does that mean? The image is smaller than the object, just the other case of the first point. And the second one is if the magnification is positive or negative. If I say the magnification is positive, then the image will be always upright or erect. Why is it so? It's because we have already stated if I take the principal axis, then if the object or the image is formed on a basis of height above the principal axis, it will be always in a positive sense. So, for magnification, it is always positive for concave lenses since they always form a virtual and erect images. When we studied the image formation in case of concave lenses, we have already inferred that, isn't it? Almost all cases they form virtual and erect images. But what in case of the other lens, that is convex lens? In case of convex lens, magnification is found to be negative. Why is it so? It is because in case of convex lenses, always they form real and inverted image. That is, inverted image means if I consider this as a principal axis, always the image will be formed instead of upside, it will be formed on the downside, isn't it? So, I get inverted images and it is below the principal axis. So, in that case, I will be always having inverted image and always my magnification will be negative. So, magnification in case of concave lens would be always positive, and if the magnification is negative, I can clearly infer or I can clearly derive that it would be a convex lens. So, when the questions come, you need to understand from the facts or also from the facts as well as in the numericals, you need to have some thought how the magnification changes, how the magnitude changes. Then only you can find easily or infer easily what kind of lenses I have used. Is it a concave lens or a convex lens? And finally, the power of a lens. Till now we have dealt with different types of mirrors, lens, their applications, their image formation, etc. So, how do we define power? In terms of general work, we define power as rate of doing work, isn't it? Power means work divided per time, or how much work I am able to do in a particular time. That is called as, in terms of energy or work, we define power. And how do you refer the power of a lens? Suppose you may be saying that your father or mother is having spectacles. If you may be saying that she is having certain power, isn't it? So, we may be dealing it with in a specific chapter later, but we need to understand for that what do you generally mean by power. So, power of a lens is termed as the reciprocal of focal length. It is represented by the capital letter P. So, P equals reciprocal of focal length, that is 1 by f, as you can see here. So, P equals 1 by f. So, SI unit of power is diopter or capital D. So, focal length is being generally represented by the unit meter. So, meter inverse is here, the SI unit of power, here is in diopter. So, if I ask you to define what do you mean by 1 diopter, how could you infer from this particular calculation? I can say as 1 diopter is the power of a lens, and which was the SI unit of focal length? It's meter. So, if I consider it as a unity, 1 diopter is the power of a lens whose focal length is 1 meter. As we have said earlier, the power of a convex lens is positive and power of a concave lens is negative depending upon the focal length. So, power always relate the focal length of a particular lens and how it varies depending upon different cases of concave and convex lens.